No questions. Let us proceed further. Can you see this?
Yes, sir.
Continuous stirred tank reactors are open systems that operate on a steady-state basis. Reactants are continuously introduced into the reactor, while products are continuously removed. CST are very well mixed, so the contents have relatively uniform properties like temperature, density etc. throughout. Also, conditions in the reactor's exit stream are the same as those inside the tank.
So do you understand what is a CSTR or mixed flow reactor? Hmm? So continuously feed is coming and continuously product is being removed. In the batch reactor, we dumped the feed. All of the feed was dumped in that reactor. And then we close the reactor. The reaction proceeds for the specified time, which is called reaction time. And then at the end of that reaction, we remove all the products. So that's a batch reactor. In the continuously feed is coming in and continuously product is being removed. So input flow rate is equal to output flow rate. That is why the level of the reactor can be maintained constant. Volumetric flow rate of the feed is equal to volumetric flow rate of the product. So is the difference between batch reactor and CSTR or mixed flow reactor clear to all of you?
Yes, sir.
Okay. So we were looking at the derivation yesterday. We'll continue from there. Okay. So ideal CSTR or mixed flow reactor. So you have continuously feed coming in. It may be one stream. It may be two streams. Doesn't matter. It's the feed we are representing as feed here. So feed comes in continuously and product is removed continuously. Here I have shown product at the top. That is normally the case and that is the way to maintain the level in the tank. But bottom में भी किया तो level control करना पड़ेगा. That's a control system problem. So and in that case, if the feed concentration is say Ca naught, right? Here it is Ca naught, and the moment it hits the reactor or reaction volume, it becomes Ca, which is the product concentration. So feed concentration is Ca naught, product concentration is Ca, and the moment the feed enters the reaction mixture, it becomes concentration of A becomes Ca. So it drastically, suppose this is 10 moles per liter, and suppose this is say 1 mole per liter. So immediately on mixing in the reaction mixture, the concentration reduces from 10 moles per liter to 1 mole per liter. So when you have C naught as 10 mole per liter and C equal to 1 mole per liter, what is the conversion? कन्वर्जन कितना होगा? हाँ,
Could you please repeat, sir?
when the feed is at Ca not equal to 10 moles per liter and product in the product Ca is 10 moles 1 mole per liter, what is the conversion of A? How do you calculate conversion?
90%.
Right. So Ca naught minus Ca upon Ca naught. So 10 minus 1 upon 10, that is 0.9 और 90% conversion अगर हमने लिया reactor में, which is what is desired beyond maximum conversion in the reactor to the product. So in that case, the moment the feed hits the reactor or reaction mixture, the concentration reduces to Ca. So what will happen to the reaction rate? What is the reaction rate? Right? Any order can be 1, 2, 3, doesn't really matter, 1 or 2, 1, 1.5. So the moment it hits the reaction mixture or it mixes in the reaction mixture, what will happen to the rate? Rate will be good or bad? What will happen to the rate? Suppose as instead of 10, I have 1 C concentration. So the rate will decrease. Ideally, I should get this rate K into 10 raised to the power of n, but I'm not getting this one in the CSTR. In the CSTR, I'm getting K into 1 raised to the power of n. समझ रही बात difference? And that's this we'll see when we look at PFR. In PFR, we can get this much. In CSTR, we can get this much. Okay, so this is what we can get in PFR. This is what we'll get in MFR. समझ में आ रही है बात? Okay. Question नहीं है तो let us proceed further. So when you say steady state, there is no change with time. So when we are assuming perfect mixing, so concentration is same throughout the reactor, which is Ca. So if you write material balance for the limiting reactant, input minus output minus disappearance plus generation equal to accumulation. Generation is 0 because we're talking about limiting reactant, so it is 0, and accumulation is 0 because we're talking about steady state. Right? So now we can write input, output, and disappearance. So molar feed rate of A, that is input, feed rate is Fa0, that is given, and that we know it is equal to Ca naught into V naught. V naught is the volumetric flow rate of the feed. Okay? So input of A is essentially Fa naught into 1 minus Xa naught if Xa naught is not equal to 0. If it is Xa not equal to 0, कभी कभी क्या होता है रिसाइकल स्ट्रीम आता है तो कन्वर्जन थोड़ा रहता है, रिएक्टेंट 100% नहीं रहता है, थोड़ा प्रोडक्ट भी रहता है. But in this case, if there is no conversion or there is a pure reactant in the feed, it is Fa naught. If it is not pure, then it is Fa naught into 1 minus Xa naught. Any questions on equation 2? Okay. Then output of A, continuously input आ रहा है, continuously output जा रहा है. Moles per liter is again Fa. यहाँ पर input था Fa naught, output is Fa. Fa is in moles per liter, moles per unit time, sorry, moles per unit time, and that is nothing but Fa naught 1 minus Xa. And we are taking this case where we are assuming that initial conversion is 0. So Fa, that is moles per unit time of A, at output is essentially Fa naught into 1 minus Xa, which is nothing but this into V naught. Right? So Ca into V naught लिया तो Fa हो जाएगा, Ca naught into V naught लिया तो Fa naught हो जाएगा, and 1 minus Xa. यही दिखाया मैंने यहाँ पर. Okay, let me remove that. So Ca equal to Ca naught 1 minus Xa किया, V naught से multiply किया तो we get Fa equal to Fa naught 1 minus Xa. ठीक है? Any questions on equation 3? Okay, so
हेलो सर.
yeah.
सर वो हमने एक्स ए नॉट क्यों कंसीडर किया है वो नहीं समझा.
हाँ, क्यों कंसिडर किया है? So many times what happens, reaction, if you take a reactor, and this conversion is suppose say, बहुत बार होता है कि conversion is not 90%, it is say 40%. तो unreacted जो रहता है यहाँ से रिसाइकल किया जाता है. रिसाइकल किया तो यहाँ पर कन्वर्जन जो रहेगा दैट इज एक्स ए नॉट. That is general case, but you have taken a specific case where you assumed Xa not equal to 0. That means there is no recycle वगैरह. We are assuming this case.
ओके सर.
ठीक है? In practice 100 में एक continuously नहीं होता है, recycle करना पड़ता है. So many systems recycle is done, and you must have seen in CPT वगैरह. देखा था कि CPT में unreacted stream is returned back to the reactor because conversion is not significant or the conversion is low. So in such cases we have to consider Xa naught, but we are not going to look at that because that is little थोड़ा कॉम्प्लिकेशन बढ़ जाता है, इसीलिए हम अज्यूम कर रहे हैं Xa naught equal to 0. ठीक है? So disappearance of A bar reaction, we have seen it before also, batch reactor में moles per unit time is nothing but minus rate of reaction of A into volume of the reaction or reaction mixture. And if you take the units, RA minus RA का units है moles per unit volume per unit time and into volume किया तो we get moles per unit time. So you have all the terms with units of moles per unit time. And at steady state I have already said accumulation equal to 0. So if you substitute all these terms in equation A, जो ये अपना ये है general material balance equation, so what you get is Fa naught 1 minus Xa naught minus Fa naught 1 minus Xa. ये general लिखा है मैंने. This is general term, right? When there is initial some conversion is there. तो थोड़ा ये different आएगा और कुछ नहीं. You can see that. Minus Fa naught 1 minus Xa minus of minus Ra into V plus 0 equal to 0. तो Fa naught cancel हो जाएगा. So what you get is Fa naught terms combine कर दिया. You get Xa minus Xa naught. So essentially what you get is here you will get Xa minus Xa naught. यहाँ पर Xa naught अगर 0 लिया तो Xa हो जाता है. इतने फर्क है. Equal to minus Ra into V, or you can write Fa naught into delta X final minus initial conversion equal to minus Xa minus Ra into V. अगर ये 0 रहा तो it will be like just Xa. So what you can write is you can bring V here and you get Fa naught here and you get V upon Fa naught equal to delta Xa upon minus Ra, and this is nothing but tau upon Ca naught. By definition we have seen that tau is equal to क्या था definition में? Is how we define tau. So V upon Fa naught is equal to tau upon Ca naught.
V upon V naught sir.
वो भी है but we are writing in terms of Ca naught now. दोनों है. Okay. So V upon Fa naught is equal to, we can write if Xa not equal to 0, Xa upon minus Ra. And this for any value of epsilon A. We have not assumed anything about epsilon A. We are writing general equation. right? So tau is equal to क्या हो जाएगा यहाँ, if you take this equation 1/2 is equal to v/v0, or v CA0/FA0 is nothing but CA0 into XA/-RA from this equation 8. अगर XA0 रहेगा तो यहाँ पर क्या हो जाएगा, इंस्टेड ऑफ XA इट विल बी डेल्टा XA और कुछ नहीं, अगर इनिशियल कन्वर्शन 0 नहीं रहा तो. ठीक है, एनी क्वेश्चंस ऑन इक्वेशन 10? Okay, so if you put XAI equal to input conversion or initial conversion, and XAF equal to final conversion, we can write the same thing as V/Fa not equal to delta XA minus RAF. अब RAF के लिए, because we are taking always at the concentration in the product, CA का concentration जो है यहाँ पर जो लिया था हमने, we are always taking this value of RA, so it's the final concentration of A in the product. So that is a minus RA at the final value of CA. And write this as XAF minus XAI upon minus RA. तो सेम इक्वेशन लिखा है, कुछ नहीं है यहाँ पर. XAI इक्वल टू नॉट जीरो लिया है हमने, अदरवाइज इट इज सेम इक्वेशन एज इक्वेशन 10. ठीक है, एनी क्वेश्चंस ऑन इक्वेशन 12? Okay, so for constant density systems, you can write CA equal to CA0 1 minus XA or XA equal to CA0 minus CA upon CA0. You can write in terms of CA also, tau upon CA0, ये जो है यहाँ पर equal to V upon FA0, XA upon minus RA, or CA0 minus C upon C0 minus RA. So you can write in terms of conversion or you can write in terms of concentrations. Now this is for epsilon A equal to 0, because we have taken this equation of CA. Or we can write this as tau is equal to V upon C0, V upon V0, or CA0 XA upon minus RA, CA0 minus C upon minus RA. Any questions on equation 14? Okay, so then we, as usually, plot the equations. Equation 8 ये था हमारा और equation 10 ये था. So we'll plot these equations because ultimately we do some graphical integration. So we plot 1 upon minus RA versus XA, right? So ये जो लिया हमने, डिनोमिनेटर माइनस RA है और न्यूमरेटर में XA है, राइट? तो टाउ अपॉन CA0 लिया तो इट इज XA अपॉन माइनस RA, तो ये लिया हमने. So we plot 1 upon minus RA on the y-axis and XA on the x-axis, and you'll get something like this curve. Points may be something like this. And in this case, if you want to have the value of the right hand side x upon minus RA, we actually have to take a point, any point here, जो XA का value रहेगा, and get the area of the rectangle. ठीक है, any questions on this graph?
So could you explain the graph once again, please?
We have equation is tau upon CA0 is equal to, ये आपने CA0 यहाँ लाया लेफ्ट हैंड साइड में, तो बचा XA upon minus RA, right? So what we want is ultimately we want this value XA upon minus RA. So what we do is we plot 1 upon minus RA on the y-axis and XA on the x-axis. बैच रिएक्टर में क्या किया था हमने, याद है किसी को? Let me show you that. In the batch reactor, we had done the same thing, almost same thing. 1 upon minus RA versus XA. ये curve आया हमारा. So this is the curve we got. And we took area under the curve. Right? We have taken this area under the curve. Why? Because it's an integral here. Understand the difference between batch reactor and mixed flow reactor. Equation is almost same. यहाँ पर tau है, यहाँ पर t है, CA नॉट है, यहाँ पर tau का CA नॉट लिया हमने, इंटीग्रल dx by minus RA. So that's why integral is always area under the curve. This is what you should know from mathematics, right? When you want to find graphically integral value, you always plot the curve y versus x and find the area under the curve, and that is the value of the integral. Okay. Now if I look at this equation, this is almost similar equation. Tau वहाँ t था, c naught भी था. यहाँ पर instead of integral we have xa upon minus RA. There is no integral, it is xa into 1 upon minus RA. Difference समझो आप.
Yes, sir. But why is the entire rectangle considered as tau upon CA naught?
Because it is not integral, it is xa into 1 upon minus RA. So this is 1 upon RA minus RA, and this is xa. So how will I find that value?
Okay, sir. Yeah. Sorry, I understood.
I have to multiply xa
Yeah.
by 1 upon minus RA, and that is for a particular value of xa. If I take a different value of xa, I'll get different area. Then this is the area. So depending on the conversion, now this is the value of xa. For this value of xa, I'll get different value of tau upon CA naught. Similarly, I can do same. I can take another value, and I'll get different area again. Same thing I can do for batch reactor also, right? xa change किया तो मेरा value change होगा, area change होगा वहाँ भी. But in this case, we have to take a product of y into x because it's nothing but y into x. 1 upon RA is y,
Yes.
and x is x. The product of y into x, it is not integral, and that is why I have to take total area, rectangle area, not area under the curve. Difference समझ में आया लोगों को? Batch reactor and CSTR. Right? So if I look at this batch reactor, if I want different value, suppose I want at this point, okay, let me take it here. Suppose I want this value, so then I have to have area under the curve up to here only. If my value of xa changes, and this is the area. Right? So depending on xa value, area will change here also, there also, but here I have to take area under the curve. In the CSTR or mixed flow reactor, I have to take rectangle area. So if you compare this area is going to be always less than that area, right? बराबर है? If I draw the
Yes,
same
sir.
area of the rectangle, ठीक है? So what does this mean? I'm going ahead now. But I'm just trying to explain, that means tau बढ़ रहा है हमारा, C0 तो same ही है. So if area is changing, that means my tau is increasing. I'm not changing CA0. So what is happening is, that means I need a bigger area for the CSTR than for the batch reactor, or bigger volume. Tau is nothing but V upon V0. ये tau बढ़ते जाएगा मेरा. That means volume of the reactor बढ़ते जाएगा. ये reactor volume is this. But that we'll see later. But understand the difference.
सर
Yeah.
सर ये सेम कन्वर्जन के लिए वॉल्यूम ज्यादा लगेगा ना?
Yes. We'll see that comparison बाद में देखेंगे, हम derive भी करेंगे. But I'm just trying to explain to you why it is more graphically. ठीक है? Is this clear? Difference between batch reactor and mixed flow reactor or CSTR, and why this is more? Because ultimately you saw that thing, right? The rate of reaction is lower in a mixed flow reactor than in PFR because of this thing. PFR behaves similar to batch reactor. We'll see later. Okay, so I'm just jumping ahead, but just trying to bring out, because हम area plot कर रहे हैं और we are finding out the value of tau. Essentially, we are trying to find the value of tau from all this thing, and that will tell us what is the size of the reactor. Any questions? Okay, so constant density का इक्वेशन ये था हमारा, right? CA0 minus C upon वगैरह वगैरह. So if we plot that equation 1 upon R minus RA versus CA0 CA, तो यहाँ पर भी कर्व आया हमारा, पॉइंट में भी समथिंग लाइक दिस. वहाँ पर हमने क्या किया था, सेम कर्व के लिए वी फाउंड द एरिया अंडर द कर्व बिटवीन CA0 एंड CA. यहाँ भी एरिया कम आएगा, यहाँ पर वी आर फाइंडिंग एरिया ऑफ रेक्टेंगल. सेम थिंग, बिकॉज वहाँ पर भी जो है इक्वेशन जो है इज नथिंग बट y इंटू एक्स. इफ यू प्लॉट 1 अपॉन माइनस आर ए वर्सेज CA0 minus CA is the numerator and 1 upon R is minus R is the denominator. So I'll get directly tau value here. और उससे हमारे को रिएक्टर वॉल्यूम मिल जाता है. So if I change CA value, suppose I take different value of CA, then what will happen is area will change. So if I take a different value of CA, the area will change, and that will change the reactor volume. What is the difference between batch reactor and mixed flow reactor? ठीक है. So let us derive some equations for different order reactions. जैसे फर्स्ट ऑर्डर रिएक्शन लिया, जैसे हमने बैच रिएक्टर में लिया था, राइट? फिर डन यूनिट 2 में पूरा बैच रिएक्टर का जीरो ऑर्डर, फर्स्ट ऑर्डर, सेकंड ऑर्डर डेरिवेशन वगैरह किया. सिमिलरली फॉर मिक्स्ड फ्लो रिएक्टर, माइनस आर इज इक्वल टू के इंटू सी ए लिया हमने, टाउ इज इक्वल टू सी नॉट माइनस सी अपन माइनस आर ए, सब्स्टिट्यूट जस्ट वैल्यू ऑफ माइनस आर ए, फिर इज के इंटू सी ए. इट्स वेरी सिंपल, इंटीग्रल नहीं आएगा कभी. Batch reactor will have integral, mixed flow reactor will never have integral. Difference understand करो. Okay, and CA लिया तो CA naught 1 minus XA, so you can write CA naught XA equal to CA naught minus CA. If you substitute किया, so what you get is CA naught into XA upon, this is K, CA naught 1 minus XA. तो in terms of XA we can write K tau, K इधर लेके आ गए लेफ्ट हैंड साइड में. What you get is CA naught minus CA upon CA or XA upon 1 minus XA. And this is for epsilon A equal to 0 because we have taken this value of CA. So mixed flow reactors के problem थोड़ा easy होते हैं because there is no integral. You don't need to integrate, you just need to substitute the value of minus RA and you can calculate tau values. Any questions on equation 17? Okay, so now if you take variable volume reactor, V equal to V naught 1 plus epsilon XA, और we can write N equal to N naught 1 minus XA को ये सब डेराइव ही कर रहा हूँ मैं, पहले भी किया हमने. C equal to C naught 1 minus XA upon 1 plus epsilon XA. तो you can write C in terms of epsilon A. फर्स्ट ऑर्डर रिएक्शन ये लिया हमने जो ऊपर था और उसमें हमने CA का वैल्यू फॉर वेरिएबल वॉल्यूम के लिए ऐड किया. तो व्हाट यू गेट इज K tau is equal to XA 1 plus epsilon A upon 1 minus. इंस्टेड ऑफ दिस टर्म ये एक्स्ट्रा टर्म आ जाएगा. अदरवाइज इट वाज XA upon 1 minus XA. रिमेंबर दिस XA upon 1 minus XA का फिर ऊपर में एक टर्म आ जाएगा, बाकी सब सेम रहेगा. ठीक है. एनी क्वेश्चंस ऑन इक्वेशन 19?
सर इक्वेशन 19 के स्टेप्स जरा रिपीट करते हैं क्या?
क्या?
इक्वेशन 19 के स्टेप्स रिपीट करते हैं क्या?
ओके, सो ये इक्वेशन 17 था हमारा. नाउ वी आर गोइंग टू राइट फॉर एप्सिलॉन वैल्यू. सो ये इक्वेशन पहले भी डिराइव किया हमने 18 वाला, राइट? C equal to CA naught 1 minus XA upon 1 plus epsilon XA. Right, we have done this before also. So we are just substituting for CA in that equation. और इसमें डाल रहे हैं, सॉरी, रेट इक्वेशन में. सो K इंटू सी ए का जब K इंटू सी ए नॉट 1 माइनस XA अपन 1 प्लस एप्सिलॉन XA, और यहाँ पर सब्स्टिट्यूट करने वाले हैं. टाउ इक्वेशन था CA नॉट XA अपन माइनस 1 माइनस आ रहा था. CA नॉट XA है और ऊपर ये सिर्फ इसको सब्स्टिट्यूट किया हमने यहाँ पर माइनस आ रहा इन टर्म्स ऑफ एप्सिलॉन A. Because this is general, any epsilon. So we are substituting CA in terms of CA naught 1 minus XA upon 1 minus 1 plus epsilon XA. Substitute किया तो ये इक्वेशन मिल जाएगा. So if it is gas phase reaction, we can use equation 17. If it is liquid phase reaction, we can use equation epsilon एक liquid phase के लिए 17 यूज कर सकते हैं और गैस फेज रहा तो 19 यूज कर सकते हैं. ठीक है रितेश?
यस सर, क्लियर.
ओके, सेकंड ऑर्डर रिएक्शन में कुछ नहीं है, वैसे ही सब्स्टिट्यूट करने का है. वैल्यू ऑफ यहाँ पर एप्सिलॉन A इक्वल 0 के लिए लिया है, उसको कॉम्प्लेक्स हो जाएगा एनी वैल्यू एप्सिलॉन A के लिए. सो माइनस आर इक्वल टू K CA स्क्वायर. CA का वैल्यू डाला C नॉट होल स्क्वायर 1 माइनस XA होल स्क्वायर एंड टाउ इक्वल टू CA नॉट XA पर माइनस आर. यहाँ पर सब्स्टिट्यूट किया माइनस आर का K CA नॉट स्क्वायर 1 माइनस XA होल स्क्वायर, और इसको रीअरेंज किया तो K टाउ के इधर आ गया CA नॉट माइनस CA अपॉन CA स्क्वायर. ये कुछ ये साइड लिया हमने, ये नहीं लिया, XA के टर्म्स में नहीं लिया, CA के टर्म्स में लिया. तो दिस इज सेकंड ऑर्डर इक्वेशन, व्हाट यू कॉल दिस क्वाड्रेटिक इक्वेशन. इसको इस साइड में लेके आ गए K of CA square is equal to CA naught minus CA. We can solve for CA by using this equation is like ax square plus bx plus c equal to 0 लिया तो you can find the value of ca. ठीक है, जनरली सेकंड ऑर्डर कुछ नहीं आता है, थोड़ा कॉम्प्लेक्स रहता है, दैट्स व्हाई यू मोस्टली गेट फर्स्ट ऑर्डर इक्वेशन और रिएक्शंस एंड प्रॉब्लम्स easier to solve. Any questions on batch reactor and mixed flow reactor? Okay, if there are no questions, then we'll go to plug flow reactor. So plug flow reactor is essentially a tube. It can be small diameter, it can be big diameter, doesn't matter. It's basically a tube or pipe. So feed is concentration Ca naught, flow rate is Fa naught, and initial concentration, initial conversion हमने 0 लिया है यहाँ पर. In volumetric flow rate is V naught, and the final concentration is CF, FAF, XAF, and VF. So if you take any slice of this tube of volume dV, in this case we can write, because we are doing derivation now, feed flow rate as FA लिया हमने, यहाँ पर FA naught था but यहाँ पर FA रहेगा, and what comes out is FA naught plus DFA. DFA may be positive, it may be negative. Reactant लिया तो negative रहेगा, product लिया तो positive रहेगा. यहाँ पर reactant तो negative आएगा. Okay? So if we plot conversion versus length of the reactor, in this case length is important because length is volume, because area is constant. So what you get is conversion versus time लिया तो you get some curve like this, and conversion will continuously increase as you go in the reactor from the L equal to 0 to L equal to L. और अगर concentration plot किया हमने, suppose I plot concentration, concentration कैसे आएगा? Any guesses? How does the concentration curve look like? Okay, concentration curve will be something like this. This will be Ca naught, and this will be Ca. It will not be exactly like this. थोड़ा curve आएगा. It will depend on the rate of reaction over रहेगा, but it will be like this. The concentration will continuously decrease as the reactant flows from left hand side to right hand side. And why is that? Because conversion is increasing, right? Conversion increase हो रहा है तो Ca is equal to Ca naught 1 minus Xa. As conversion increases, concentration decreases. बराबर है?
Yes, sir.
Yes,
Right.
sir.
So if you look at rate of reaction at any point, right? So minus Ra suppose I take first order reaction, doesn't matter. So K into Ca. Right? So Ca का value सब जगह change हो रहा है तो rate of reaction is going to continuously decrease. जैसे Ca का value decrease होते जा रहा है, वैसे rate of reaction is also going to continuously decrease as the reaction mixture goes from entrance to exit. And that is why I was saying, so you'll get maximum reaction rate here because the value of concentration is Ca naught. यहाँ पर कम हो जाएगा और कम हो जाएगा, कम हो जाएगा, right? Whereas if you look at mixed flow reactor में क्या था rate of reaction? It was at this value because that was exit concentration. So mixed flow reactor में minimum rate of reaction मिलता है, and plug flow reactor you get much higher than mixed flow reactor rate of reaction, because यहाँ पर ज़्यादा रहता है CA तो ज़्यादा मिलता है. समझ में आया डिफरेंस बिटवीन प्लग फ्लो रिएक्टर एंड मिक्स फ्लो रिएक्टर?
सर वो लास्ट पॉइंट एक बार फिर से बताओ ना कि कन्वर्जन क्यों ज्यादा होता है.
ये क्वेश्चन पता है आपको?
हाँ सर.
Right. So you have initially you have concentration CA naught here. The rate of reaction यहाँ ज़्यादा रहेगा. Conversion is 0. बराबर. So initially conversion is 0, concentration is maximum, rate of reaction is maximum. Right. तो थोड़ा conversion हो जाएगा. Suppose यहाँ पर 10% हो गया. तो CA कम हो जाएगा 10%. फर्स्ट ऑर्डर लिया हमने तो CA कम हो जाएगा. राइट. CA कम हो जाएगा तो रेट ऑफ रिएक्शन कम हो जाएगा. बट कन्वर्जन इज इंक्रीजिंग कंटिन्यूसली. यहाँ पर कन्वर्जन 10% था, यहाँ पर 20% हो जाएगा, यहाँ 30% हो जाएगा, 40%, 50%. तो कन्वर्जन इज इंक्रीजिंग एंड एट द सेम टाइम concentration is decreasing because these two are linked.
नहीं ये पॉइंट नहीं सर, वो कि जब हम उसे CSTR के कन्वर्जन से कंपेयर करते हैं तब.
क्या करते हैं?
सर वो कन्वर्जन इसका ज्यादा क्यों होता है CSTR से?
Because concentration is higher ना. In the PFR concentration is different at each point. यहाँ पर different है, यहाँ पर different है, यहाँ पर different है, यहाँ पर everywhere the concentration is different. Because यहाँ पर जिससे suppose I enter at time t equal to 0, and this is at suppose it takes me 1 minute to come out, right? And tau is equal to V upon V naught है हमारे पता है हमारे को. Is defined when we define space time, right, or resistance time. So I know the volume of the reactor. I know the volume at floor. I can find out time tau, right? So if it takes 1 minute to go from here to here, if I take any parcel of fluid here, it will take me it will take that parcel of fluid 1 minute to reach here. And while it is traveling from here to here, it is reacting, continuously reacting. बराबर. कॉन्सेंट्रेशन में मैक्सिमम है, यहाँ पर धीरे धीरे कम होते जा रहा है, कॉन्सेंट्रेशन कम होते जा रहा है. जैसे कॉन्सेंट्रेशन ज़्यादा रहेगा तो रेट ऑफ रिएक्शन ज़्यादा रहेगा, बिकॉज यू सीन दिस रेट ऑफ रिएक्शन. राइट. तो कम होते जाएगा, कम होते जाएगा, कम हो जाएगा. यहाँ पर मिनिमम मिलेगा और यहाँ पर मैक्सिमम कन्वर्शन रहेगा. Does that answer your question, Devendra?
या सर.
Right? And that is what I was saying in the advantage. जैसे बताया मैंने कि इनमें CSTR you get मैक्सिमम वॉल्यूम रखना पड़ेगा रिएक्टर का, बिकॉज कॉन्सेंट्रेशन जो रिएक्टर का है जहाँ रेट कैलकुलेट करते हैं CSTR में एग्जैक्ट एग्जिट कॉन्सेंट्रेशन. whereas in a PFR rate is calculated at different concentrations throughout. It keeps changing. तो यहाँ पर it will match with CSTR rate of reaction, but यहाँ पर सब जगह it will be higher than CSTR rate equation. So minus RA of PFR is going to be always greater than minus RA of CSTR for the same exact concentration. समझा क्या?
यस सर.
Okay, any other questions? Because this difference you should understand between PFR and mixed flow reactor. We'll see all derivations, but as I'm trying to explain you the concept. Okay. So then we'll do again the same material balance for the limiting reactant. So input minus
सर
yeah.
सर CSTR में कंसंट्रेशन जो इनिशियल होगा वो ज्यादा होगा ना.
CSTR में मैंने बताया था आपको.
हाँ.
The moment the feed hits or reaches the reactor, its concentration reduces to exit concentration.
ओके सर.
यहाँ पर CA नॉट है, यहाँ पर ऑलवेज CA है.
हाँ.
यहाँ पर सब जगह CA है. दैट मीन्स यहाँ अगर मैंने 10 मोल्स पर लीटर लिया और अगर 90% कन्वर्जन है, तो मोमेंट इट हिट्स दिस थिंग इट बिकम्स 1 मोल पर लीटर. because the flow rate is always very less compared to the volume of the reactor. And that is why the rate of reaction is low in CSTR compared to PFR for the same exit concentration.
Okay, sir.
Okay, so same thing we are going to do. Accumulation is 0, steady state liya humne. Generation is 0 because we're looking at limiting reactant. So input of A is nothing but FA, जैसे पहले लिया था हमने, यहाँ पर डिफाइन किया. FA is input at this in this slice of the reactor because we are going to integrate. यहाँ पर concentration continuously change हो रहा है, conversion continuously change हो रहा है, because that's why we cannot take like mixed flow reactor. We have to integrate. तो यहाँ पर feed है FA और output input is FA and output is FA plus DFA. Right? So input is FA and output is FA plus DFA. DFA is negative in this case because we are looking at reactant. So if we take CA equal to CA naught 1 minus XA and multiply by V naught, we get FA equal to FA naught 1 minus XA. And if we take DFA, derivative of this FA is equal to nothing but derivative of FA naught into 1 minus XA. And that gives us DFA equal to minus FA naught because FA naught is constant into DXA. ठीक है, equation 5. ठीक है, so then disappearance by reaction is similar to what we have done before, minus RA into dV. यहाँ पर dV लेंगे because we are taking a small slice of the reactor. Right? And then we substitute input output disappearance in the equation 1. And what we get is input is FA and output is FA plus DFA, and disappearance is minus RA into V. FA cancel हो गया and FA DFA का यहाँ पर substitute किया हमने, minus FA naught into DXA minus RA into dV equal to 0. ये सब पॉजिटिव हो जाएगा, साइन वाइन का चले जाएगा. What you get is FA naught into DXA is equal to minus RA into dV. So now what we need to do is we need to find the total conversion. So we need to integrate because we are taking only small slice of the reactant or reactor. So now we need to find कि अगर वॉल्यूम मेरा 0 से V तक टोटल वॉल्यूम होता है तो what is the value of XA, and that's why we have to integrate dXA upon minus RA 0 to XA because XA is changing it. XA is a function of length or function of volume, and minus RA will also be a function of length or volume, और जैसे ये वॉल्यूम लिया तो XA आएगा. Right? So we need to integrate from 0 to XA, final XAF, and volume is 0 to V. ठीक है, so we get V upon FA naught total volume is equal to tau upon C naught. By definition this is what it is equal to integral 0 to XAF dx upon minus RA. And this is for any value of epsilon A. Any questions on equation 7? ठीक है, if there are no questions then let us write this in different form tau के terms में. V upon V naught, V into CA naught upon FA naught is equal to CA naught लेना पड़ेगा यहाँ पर tau के लिए, integral 0 to XA F dx upon minus RA. So this is the equation for plug flow reactor. And if you compare with batch reactor, we had T batch time is equal to CA naught integral 0 to XA dx upon minus RA. So if you compare this and this, it's exactly same equation. So batch reactor and plug flow reactor behave in the same manner. Performance of the batch reactor is the same as the performance of the batch reactor and plug flow reactor, not mixed flow reactor. ठीक है, any questions? Okay, so if you compare with mixed flow reactor, you take the equation mixed flow reactor, tau is equal to V Ca naught upon Fa naught, Ca naught X upon minus Ra. So ये था, if you see this and this, this is the same as this one, and if you see this, what is the difference between these three? Difference है कुछ similarity है?
So no difference.
Hmm?
It's the same. If we solve the integral, we'll get that.
No, we'll not get the same thing. अभी बताया मैंने. This is area under the curve.
Yes, sir, graphically, but if we solve from limit 0 to xa, we will get Ca naught into xa.
No, because Ra is not constant.
सर वॉल्यूम कम लगेगा PFR
वो तो है. I'm just trying to say कि equation is similar, but what you'll see is batch reactor में integral आएगा, PFR में integral आएगा, और CSTR में integral नहीं आएगा. Terms are same, Ca naught, dxa, xa. Here is nothing but xa minus 0, right? Minus Ra, minus Ra, minus Ra. The terms are same, but in the mixed flow reactor, you'll not get integral. In the batch reactor and PFR, you'll get an integral. And that's the way to remember it if you want to remember the same equation, because these are all called performance equations, right? So batch and PFR are the same equations. Performance of batch and PFR is the same. If I take a batch reactor and calculate T, and I take a performance PFR and calculate tau, I'll get the same value for the same conversion, same Ca naught. But I'll not get the same tau for mixed flow reactor, because now I'm getting area under the area of rectangle, not under the curve. समझ रही बात?
Yes, sir.
Because we have done the same thing. बैच का प्लॉट किया था, वही किया था हमने, वही करने वाले हम यहाँ पर. किया नहीं है, दिखाया नहीं मैंने, बट इट इज सेम थिंग. यहाँ नीचे है. We'll see it tomorrow. Time हो गया. But understand the similarity between equations and difference between equations. Batch and PFR is the same equation. MFR is non-integral but same terms. ठीक है, any questions? डाइजेस्ट करना पड़ेगा आपको, इट्स नॉट सो इजी.